stereo.
Today, we'll talk about finding subnet facts about a subnet that already exists, converting subnet masks. So when you see a mask in some output on a device or in some documentation and you need to think about it a little differently, often you need to convert mask formats. So we'll talk about how to do that. It's not hard. And then we'll talk about finding facts about Class A, B, and C networks, which is really the last 20 minutes of today, which sets us up for day 2, which is much more about design and new projects. All right. So, for instance, when you start a new project, you start with a block of addresses that you then subdivide or subnet into usable sizes for your project. So we'll talk about how to find all subnets of one big block to create a bunch of smaller blocks or subnets so you can deploy those in a new part of your network, for instance. And part of understanding that is working with subnet masks. So we'll talk about how to interpret masks and take a design perspective on those, about why you would pick one mask versus another, and then ultimately finishing up with you choosing a mask given some requirements for a new bit of the network. All right, so that's where we're headed. Now, the material has some math in it, and the approach to the course is a little bit like math class back in school. And to help you do better with that, I'd like to suggest, and I will suggest throughout the course, for you to pause each time we get to a lab exercise and think about where you are at that point in time with what I call learning stages. Learning stages just say to you, how well do I know what I just learned for the last little bit? For instance, stage 1, the learning stage, you don't know the topic well yet, so the recommendation is to go slow and you can use your notes. But at some point, you need to set those notes aside. That's stage 2. But you set them aside so you can perfect your learning, not so you can learn to go fast yet. And then finally, when you're always getting the right answer and you want to go fast for some exam, that's stage 3. So I'll get into more of that as we get into the first lab exercises, and I'll give you a little more depth on that. But I'm going to ask you to think about who you are right now with that. And experience shows that will help you learn subnetting quicker and more deeply as you go along. All right? So that gives you a little context. So in words, here's the outline today, operational view, analyzing existing subnets will take us through the halfway point today. That's most of today. And then 2 shorter topics, one on converting masks into different formats and understanding those, and then analyzing IP Class A, B, and C networks. Then tomorrow, we'll talk about, hey, let's start with, say, a private Class A network 10. How do I subnet that? What would the subnets be if I chose a particular mask? And then we'll talk about some design choices you can make having to do with choosing what mask to use when you're planning a new project. Then we'll wrap up with a few minutes about subnetting and the CCNA exam, because some of you may be headed toward the CCNA or some other exam for which you need to go relatively fast without a calculator in order to do well on the test. All right? So what about you? Tell me a bit about yourself. You should see a poll question on your screen now where subnets. You get a job, you go to the company, they've got a network. How do you analyze and understand what's already there? That's what we're about. Now, to do that, I have to pick some starting point for what I assume you do and don't know. So I picked one, and I'm going to give you a little bit of introductory and contextual information that helps us understand subnetting. Not a lot, just a little, about addressing, routing, and routing protocols for subnetting. So, context. Addressing and subnetting are intertwined with routing and what routing protocols do. All right? So we need to understand those, at least in their basic form, for us to better understand how subnetting works. So first off, what is an IP address? And we see this list of information. And that's mostly for reference, but just to talk through a few of those before I get into some examples. There are numbers. There's an RFC, a request for comment, that defines them. You don't have to go read it. You'll usually see them as item number 3 is a dotted decimal number, a decimal number, dot, another one, dot, a fourth one, 4 octets, and a dotted decimal number. I'm sure almost all of you have seen them before, but that's how we represent the 32-bit binary number. Nobody wants to write a 32-bit number or read a 32-bit binary number, so we use dotted decimal number. And it's an identifier for interface. So if you've got a desktop computer with an Ethernet card, and that's it for its network connectivity, it's got one IP address. But if you've got a laptop and it's got a Wi-Fi card and it's also got an Ethernet card and the Ethernet's plugged in and you're using Wi-Fi, it's got two IP addresses, one for each. So it's an address per interface. Routers connect to networks with lots of interfaces. So it's an address per router interface. So it's identifying an interface that connects to a TCP/IP network. And unsurprisingly, it's used as a destination and a source for packets. So we send messages in TCP/IP networks. There's a header, there's a source and destination address in the header, and that address is this IP address. Right. So let's talk about that and expand upon that just a little bit. So there's a dotted decimal number over here on the right, 10.1.1.1. Those numbers range from 0 to 255 with some different rules, but that's the kind of number you'll see in each octet. If we look at its binary equivalent, you see it over here. And I know that because I made the slide, but I also know it because I can do decimal to binary conversion where I could take this 10 decimal and convert it to 8-bit binary and see that. Now, for this class, you don't need to be able to do that. In fact, part of the point of this class is to teach you processes so you can do subnetting with no binary math, or at least no binary conversions. But if you'd like to convince yourself along the way of, hey, 10 decimal really does convert to this 8-bit binary number, if you look in the links, and pardon me while I cheat and look at my student login, if you look at the class notes link in your user interface, looking for it here. Anyway, I'll find it at the break before lab. It's not jumping out quickly, but if you follow those links, eventually you'll find the reference page that has things that are all the tables you need for doing subnetting, like a binary to decimal and decimal to binary conversion chart, the power of 2 chart, and that kind of thing. But it's linked a couple of ways in those resources over to the right. But more importantly, IP addresses, they're dotted decimal. So here's a list of some IP addresses. And if we look at their binary equivalents, you can see them over there. And there's a concept in IP addressing in which there's a portion of the address that is the same and a portion that varies in a set of addresses. There's a portion that's the same and a portion that changes amongst the set of addresses when the addresses are considered to be grouped together. That's a very broad concept. And the first broad concept like that is called a network. A network is a predefined grouping of IP addresses. And in this case, there's a thing called network 10, which is comprised of all addresses that begin with 10, and then varies some way, shape, or form in the last 3 numbers. So in decimal, they're all the same in the first octet, and they vary in some way in the last 3 octets. And that's what's designated here with the 2 different color schemes in our binary path. All right. So you're going to see that theme throughout IP addressing. Sets or groups of addresses that are consecutively numbered. The left-hand side is the same value amongst all the addresses, and the right-hand side varies from address to address to address. And when you talk about that, the first set of terms we use to describe that is the word network on the left for the part that's the same for all addresses, and host to describe the bits that differ from address to address to address as you go along. All right? So as you see, there will be a few terms that we'll talk about here and there. By the way, when you see me looking over to the side, I'm checking a second screen that has the Q&A widget and your group chat there. So I'm not just looking over chatting to somebody else. All right. Now let's think about some PCs. They're connected to a LAN switch. That's their physical connection into the network. And by design, we place them within the same set of addresses. And it says they're in network 1. They're in a grouping that, for this, this is introductory, so just to get us rolling. In the set of addresses that begin with number 1, the dotted decimal numbers that begin with 1. And so in the configuration for those 4 PCs, we see they all have addresses that begin with 1. Well, in order for those devices, those hosts, as we call them, to send packets to faraway hosts, there needs to be some router connected to that LAN as well. So here's a router called core, and it's got an interface, and that interface also has an address in the same group. So the router's connected into the group. And say the core router wants to communicate to some remote sites like this one and this one, you might have some WAN links. By the way, this jagged line is meant to represent a serial WAN link. This line with a little cloud on it is meant to represent an Ethernet WAN link. But no matter the style, this is a WAN link that might be, the core router to router B1, branch 1 might be, 100 miles, 500 miles, that kind of thing. And it needs a set of addresses, one per interface, one over here, one over here. And those are in a different grouping. So comparing the left-hand addresses to the ones on the upper center grouping, they're different. And even the bottom center grouping, there you have a third group, all addresses that begin with 5. So there's this concept with IP addresses that says whatever groups of addresses you use, when they're separated by a router, they need to be in different groups. And we'll explore that here in the next few minutes. We'll be And then say those remote branch offices have a LAN with a LAN switch. We've got more addresses whose ranges of addresses are different. All those that begin with 2 up here and all those that begin with 3 down here. Now, those are very general concepts, but this is the foundation for how IP addresses work. So keeping that in mind, we're gonna dig down in way more depth on how addressing works and how subnetting works. But that's the big idea. But before we do that, let's talk about routing and routing protocols to finish out our contextual view of the world. So how do these routers do their thing? Well, routers, their job is to forward packets. Packet is a specific term for messages sent by the IP protocol. And when I say messages, a bunch of bits that have some header and some data, and the header has the source and destination IP address. So in one way of thinking, when we're having a conversation about how the internet protocol works, we can talk about the host, and we can talk about the routers, and we can largely ignore what the LAN switches are doing that are hidden by those straight lines, what's going on a serial WAN link, what's going on inside the service provider network that creates an Ethernet over MPLS link. The discussion of IP is focused on the host and the routers as opposed to the data links. All right? So talking about IP routing, hosts think in terms of, hey, if I want to send a packet and the destination is not local, it's remote, send the packet to my default gateway. So here you go. Destination is in another group of addresses. Send it to some nearby router. We call that the default gateway. In other words, send the packet to router R1. R1 gets it. He has a routing table. And a routing table is a list of routes. The first part of the route lists the destination. So router R1 knows about all the possible sets of addresses, all the networks and subnets. And R1 knows from its perspective where it should forward packets so they get closer and closer to that subnet. So they're arriving eventually at that subnet. So R1 generically says, hey, my route says send this packet to router R2 next. Well, what does that route look like? Well, here you go. This is the route on router R2. It says, hey, to get to subnet 10120/24. And then we've got this thing over here that says 10120/24. Well, that's something we're going to explore and get very comfortable with before we're done today. That is the shorthand way to represent a subnet that represents the entire range of addresses that can be used out here. All right? And so that's what R1 is going to have in its routing table entry to forward packets to that set. And then there's some forwarding instructions, which tells router R1 where to send the packet next. In this case, it says, send the packet out your serial 011 interface, which is just an identifier for router R1's interface, to the IP address of the next router, which is router R2's IP address. So a lot more detail there, right? But an very important thing to know is that a routing table is a list of destination subnets along with this little bit. It's called a subnet mask. And the subnet ID and the subnet mask together identifies the set of addresses in that set or subnet of IP addresses. So it tells R1 where to forward packets. So you can see routing and subnetting are very much intertwined. Routing relies on there being correct and effective subnetting. So router R2 gets the packet. Router R2's route says, hey, send the packet to router R3 next. R3 gets the packet. His route says, hey, I don't need to send this packet to another router next. Let me send it directly to the destination, PC2, and router R3 does just that. So the packet that you send, or the devices send, there's a header, as I mentioned before. This is a view of the header. You don't have to memorize it, but just note there's the source and destination address. And this drawing is 4 bytes wide, so each address is 4 bytes or 32 bits long. This is a confirmation there. All right. So there's a bit on addressing and routing, but to wrap up the contextual background, we'll talk about routing protocols for just a moment. Those routers had useful routes in their routing tables, and the typical way they learn those is via something called a routing protocol. So let me walk you through an example that matches the routing we just saw. So you remember how router R3 was connected to this subnet 10120/24. And while I haven't fully defined what that means, part of that is the subnet ID and part is the mask. Subnet ID and mask. And so router R3, get this, because this interface is up and working and configured with an address, router R3 can calculate the subnet ID. And the first half of today is about you looking at those same numbers and calculating the subnet ID. All right, so you're going to be able to do the same math. But router R3 calculates the subnet ID and puts a route in its routing table for this, quote, connected subnet, the one that's connected to it off an interface. And it says, hey, it's connected to interface gigabit 0/1. So there you go. And there's no next top router. That is, there's no next router to forward to because we don't need another router. It's directly connected. All right. So that's how the process gets started. Then router R3 uses the routing protocol. The routing protocol defines messages that routers can use to tell each other about routes they know. That's all it does. There's more to it than that, but that's the basic function. So router R3 and R2 and R1 use this messaging protocol so they can tell each other, hey, I've got a route to subnet 120. So R3 does just that. So there's its connected route. Oops. So it says, I want to advertise with my routing protocol a route to subnet 10120/24, and I want to send it to this neighbor. The routing protocols have a concept of a neighbor, that is a router that is on the same link as I am. So router R3 and R2 are on the same link. R3 will not advertise routes to R1 directly. R3 is going to tell R2. R2 is going to tell R1. Right? So it's like telling your next door neighbor, and then telling their next door neighbor, and then telling their next door neighbor, and then eventually the whole neighborhood knows the rumor. It's that kind of idea. So R3 advertises that route so that now R2 has this route to subnet 10120, which sits over here, but R2's route has an interface on R2 as the outgoing interface, and the next top router is R3. All right? So now R2 has that route. And then R2 uses its routing protocol to advertise over to R1. R1 learns a route to subnet 10120/24. R1's route lists its interface as the outgoing interface. Next top is router R2, like that. So that gives you a little bit about how routing and routing protocols work. Now, for learning and studying, let's say you answered with the first answer about who you are coming into class. If some of this stuff is new to you, a great way to review between today and tomorrow is to come back to this slide and this slide. By the way, you can download the PDF while you're here today, so I encourage you to do so. And before we're done in the next 15 minutes, there'll be another term reference slide, term reference number 3. And just look at those terms and see if you can remember and review what the meanings are. Now, I probably didn't say out loud all of the terms in these 2 pages, but it's a good review and reference tool. All right? So, in thinking about this idea of individual subnets, next we're going to talk about subnetting basics. But first, as I typically do, I'll look every once in a while and see if we've got any questions in the queue. Thank you, JV, for the looking at a drawing of the network. Conceptual, just thinking about it. And then mathematical, how do we work with the numbers? You know, we see numbers in output. How can we then take the numbers, do some math against it, and come up with more useful information about a subnet? So let's start out with the topological view. So here's the idea. Just grab that loaf of bread later and start eating it, right? It's a French loaf. Maybe you break it into pieces so everybody that's coming over for dinner tonight can have a piece. Or if it's a loaf of bread that's obviously made to be cut into slices for sandwiches, you get out a good knife and you start slicing into the slices that are good for making sandwiches, right? But you subdivide your loaf of bread into a useful size or how you like to eat bread. Well, not a great analogy, but it makes the point. What we start with IP addressing conceptually is a set of addresses, and they're consecutive. So I don't want you to think of them as a blob. I want you to think of them as a line, like a loaf of bread. It's got a width, and then we're going to want to chop it up into useful sized pieces, and that is subnetting. So when we think about chopping our loaf of bread, if we need 20 slices, we're going to make them a certain size. If we only need 10 slices, we're going to make them a certain size. And so when we think, now back to real networking, think about a topology diagram, we have to think about, well, where do I need a subnet? Where do I need a set of IP addresses that's different from another set? So that's 2 sets. And it's different from another set, that's 3 sets. How many do I need? And the short version is, for the kinds of technologies we're going to get into, certainly for CCNA and Network Plus, and honestly, most of the way through the first part of CCNP, it's these 3: VLAN, serial links, and Ethernet LAN links. All right? So for instance, you've got a LAN switch. Now, this is a brief aside on LANs, not IP. But if I've got a LAN switch and I connect 6 computers to the LAN switch, the LAN switch configuration, concerned with layer 2 concepts, it places all of those ports in the same, quote, virtual LAN. Right. By default, they'd all be in VLAN number 1. And what that means is, for any of those 6 PCs, if they send an Ethernet frame in, and it's a broadcast, that broadcast is delivered to the other 5. They're part of the same Ethernet, quote, broadcast domain. That's, by definition, what a virtual LAN is. Now back to IP. From a design perspective, if those 6 computers are in the same single VLAN, they would typically be assigned an IP address from the same set or subnet that is the same range of consecutive addresses. So we've labeled that as subnet 1 up here. Now the number 1 does not have to match this VLAN 1. I just did because it would be easier to remember. But all these computers would have an address whose left-hand side is the same and whose right-hand side differs in some small way. And that dividing line is based on the mask, which we haven't talked much about yet. Whereas if I took a LAN switch and configured the top 3 ports to be in VLAN 10 and the bottom 3 ports to be in VLAN 20, that's 2 VLAN. Then for the IP configuration, I'm going to choose addresses in one subnet that I've labeled subnet 10 on the top and addresses in a second subnet that I've labeled subnet 20 on the bottom. 2 different subnets. So the question of I'm going to start with a set of addresses that are not subdivided, and I'm going to subdivide it into subnets. By the way, the word subnet means to subdivide a network. Subnet. So we're going to cut our loaf of network, if you will, into usable slices, usable subnets. We need two, one per VLAN. So continuing our discussion on the VLAN side of things, let's see, hang on. Yep. So let's take a network diagram like this. And let's just say where we see LAN switches, there's just one VLAN. Everything's defaulted into VLAN 1 in each place. So we need one subnet here, one subnet here, one subnet here for a total of 3 on the LANs. And each of these WAN links needs a subnet, so we'd need 5 subnets. But if we had the same topology diagram and it said nothing about VLANs, you don't know how many subnets you need in this design. What you need is VLAN information. So for instance, if what was on the left, maybe that's a main site, and you had several LAN switches, and you actually had 12 VLANs over here. And at these branch offices on the right, you always had 2 VLANs as your standard branch office configuration. Well, that's 12 plus 222 is 18 plus 3 for the 3 WAN links. So that's what, 21 subnets total in this design. And as you might guess, if I'm building out this network and I'm planning for subnets, you don't build it for what you know you need. You build it for what you know you need plus growth that you estimate over time, right? You've got to do some planning. But if you're showing up and this is already built and you're trying to understand your new job and your new network, you say, oh, well, this was a part of the network and they have 12 VLANs here and 2 each, et cetera. That's why they needed 21 subnets for this part of our network. All right. So let me take a look. So RC had asked about what is the difference between a VLAN and a LAN? Perfectly reasonable. So if I can find a good backdrop for that. Go back to that slide. So a LAN is a set of devices. No, because we're talking about virtual concepts, it's sometimes hard to visualize with me just waving my hands here. So let's define it this way. If I think of a LAN as a set of devices that are connected to switches, so that if any device sends a broadcast, it's received by the other device, let's call that a local area network. Now that's pretty generic, but if I took a LAN switch and I plug everything in and everything defaulted, that's one LAN, and that a broadcast from a device on any port is sent out to the other ports. Now, if I wanted to create a design like you see in the center of the drawing, the original drawing, so that I've got 2 separate LANs, I could buy 2 switches to create 2 separate LANs so that a broadcast from this device could never get down here. There's no physical path for it to get down there. LAN at the top, LAN at the bottom. But that would require purchasing more hardware. So in the mid-1990s time frame, networking vendors said, hey, we can do this just with configuration. That same idea, to give configuration flexibility. When you want to have separate broadcast domains, separate sets of layer 2 devices, separate sets of LAN connected devices, where I can group them to layer 2 level, like you see here. So virtually created LANs, virtually created sets of devices for which a broadcast by one device will reach the others in that set, and only the others in that set. All right. And so in this question, SM was asking how's that 21 instead of 18? So we got 12, 2, 2, 2 gives us a total of 18. 1, 1, 1. That's the 3 you were probably leaving out. So each of the WAN links needs a subnet as well. So let me know if that didn't connect the dots. All right. And that gets us back. That gets the questions completed. Let me There we go. All right, so talking more about this idea of a subnet then. So we say we need a subnet, but what is it? Well, first off, we're going to learn how to do the calculations, but we've got a subnet ID and mask, which together define the set of addresses in a subnet. So once you know how to do the math, you can look at that and say, oh, that means all addresses that begin 1011 something. And this is the correct use of them in that all these hosts over here on the left, they could use addresses. Oops, getting a little bit of a funny transition going on the user interface here. Say those 4 hosts use addresses 10.1.1.1, 10.1.1.2, 10.1.3, 10.1.1.4. They all begin with 10.1.1 in this case. Now, the rules differ based on that. So if you're like, well, I don't think I could have figured that out yet. Well, I haven't told you enough to if you're new to subnetting. So bear with me. You're getting. But in this case, this number at the top means all addresses that begin 10.1.1. So these 4 meet those rules, and they are not separated from each other by a router. Let me say it again. They are not separated from each other by a router. So that's the correct use of addresses in the same subnet. Addresses who are numerically in the same subnet should not be separated from each other by a router. All right? So numerically speaking, here's what's in the subnet down here at the bottom. We've got this number at the top, this shorthand. But what it means is there's an identifier that ends in 0. There's a range of usable addresses that are the numbers that end in .1 through .254. And then there's a broadcast address, which is also not usable, that's at the end of the range. So those are the 4 key facts you can learn about a subnet. You should be good at learning those and deriving those with math. That's the first 2 labs. All right? You're just getting better at that in more difficult cases. But knowing that bit of math, when we assign addresses manually or when we set up a DHCP server so these devices can learn addresses, we want to make sure they come from this set of addresses for this part of the topology. Only devices up there on the upper left should be grabbing addresses from this range per our planning. All right, so that's part of the topological view, if you will. Now, one of the reasons that's important is routing. Remember how I said routing and routing protocols are tightly intertwined with how addressing and subnetting work? Well, remember that routing table on other routers? Well, router R2, it needs to be able to have a route that says all of the addresses in that subnet are reachable out my G01 interface to router R1 next. In other words, they're over there. Routing only works if we keep addresses in the same subnet together, like you see in this drawing. Now, just to belabor the point for a moment, this is wrong. So the idea of the subnet is this range of addresses still on the bottom of the drawing. You can't take addresses from that numerical range and put one up here in the upper left and one in the upper right and one in the lower right and one in the lower left so that they're separated from each other by a router. That's against the rules. They need to not be separated from each other by a router because the routing tables now can't have one route that says, hey, all of that subnet is in one place. Now it's spread all over creation. Right? So don't do that. All right, so that's the topological view. So RC, I don't know if the other answer got you what you were asking for in the group chat, but so yes, it's really a design tool, and so routing works much more efficiently with addresses group. It may be as simple as, hey, we've got a branch office, it's got a LAN, those addresses are in the same subnet. So in order for routing to work, let's give it a subnet. It may not be anything more dramatic than that. But I'll take a look at it while you're in lab and see if there's more to offer you there. All right, so moving on, concepts. Now let's go back to that idea of a big set of addresses, like a loaf of bread. But let's represent it this time just as a box. Here's a bunch of addresses that we call a network. And that is our starting point for thinking about addressing. And we're going to subdivide it. Because let's just say that network is way more addresses than you need in one place, just like our local bread is a way bigger piece of bread than you ever need to just sit down and eat, right? So we started that one network, but then maybe we need to subdivide it into subnets. And let's say we subdivide it into 16 equal-sized subnets represented by this grid. Great. Now you can use them. Maybe you currently need to use 5 of them. You could use these, and you've got some more left for growth. All right? So you had to think about that and decide what those are, and we'll talk about that, the mechanics of that some more tomorrow, the first part of tomorrow. But another time, you might have taken a network and say, hey, I need more than 16 subnets. So if you took that network and said, conceptually, I'm going to break it into 64 subnets because I needed more. Notice these little boxes appear to be smaller, which would be true. It's kind of like, hey, if you took a loaf of bread and chopped it into 16 slices, they might be thick. If you chopped it into 64 slices, if you physically could do it, they'd be really thin slices, right? Same thing here. If you took the same network of addresses and broke it into a lot more subnets, there are going to be fewer addresses per subnet. All right? And so you'll see that, and we'll do the math on that as we go along. Or you take that same network, you break it into 256 subnets. And you might notice that in my conceptual drawings here, there are a couple of things that are true about the examples I chose. All those little subnets all look like they're the same size. And we've chosen to break them into a power of 2 number of subnets. So there's a design choice you can make where you can choose to make all your subnets the same size. And you can instead choose to make them different sizes. Totally up to the people that make up the addressing plan for your network. There are pros and cons of each. But so the drawings I've shown you are the simpler way. Nothing wrong with doing it both ways. But so far, we're just saying, hey, let's, 16 is, 2 to the 4th subnets, or the 64 is 2 to the 6th subnets, or here 2 to the 8th subnets of your original network. Now let's take the concept a little deeper with a specific example. Let's say your beginning point was this thing I'm going to call Class B Network 172.16.0.0. So what does that mean? So just take it on faith from me. That means all addresses that begin 172.16. And I'm going to give you the rules toward the end of the day that complete the discussion of, well, how would I know that? Versus just trusting you, Wendell, right? So Class B networks in general are networks that are defined as all the addresses with the same value in the first 2 octets. And you take that network then, that's like your loaf of bread, and then you subdivide it. But the unsubnetted network is represented on this slide, whereas the subnets I've represented on the next slide. We said we want to break up the network that has all addresses that begin 172.16, and let's make one that, of course, begins 172.16, but also has then a 1 in the 3rd octet. And another one that has a 2 in the 3rd octet. And another one that has a 3 in the 3rd octet. And so, in effect, we've broken it into smaller groupings. That is, subnets. All addresses that begin 172.16, here's the smaller slice. Another smaller slice, another smaller slice as we go along here. So let's define this thing called a subnet a little bit more formally. So noun-wise, it's the subset of the network. It's all addresses that begin 172.16.1 instead of just 172.16. It's the subset. But used in a different context, it's the verb. It's the process of subdividing the network. 2 subnet, 2 slice up your loaf of bread. Kind of thing. Then it's defined by numbers. So the thing that is a subnet has a subnet ID. It has a range of usable addresses. Now, why usable addresses? Because the subnet ID cannot be used by a computer. So it's reserved and not allowed to be used for sending and receiving packets. And then there's the, quote, subnet broadcast address, which is also reserved and not usable for sending and receiving packets. So we've got this idea of a subnet, and that's going to be what we do most of our calculations for, is to find that information in step 3. All right? So the subnet mask is key to those calculations. Now, the subnet mask I mentioned here and there, what it does is many things, but it defines things about the addresses in the subnet. It defines the structure. It tells us what you will generically call the prefix bits. That is, the part on the left that is the same, the bits on the left that are the same for every address in the subnet, the same value. And the host bits, which are the ones that vary from address to address to address. So you can create different numbers in the subnet. All right, so the subnet mask also defines the size of the subnet because the number of usable addresses in a subnet is calculated as 2 to the h minus 2, where h is the number of host bits as defined in the mask. And it's not just 2 to the h, it's 2 to the h minus 2 because there are 2 reserved numbers in each subnet, the subnet ID and subnet broadcast address. All right, so you will get to practice that here coming up. Just checking the queue. Nothing new there. All right, so let's talk a little bit about the math. So if I take any address in math, you get a call, you're working the help desk, you get a call, you're working first level support, you get a call, you're doing the job, you're just looking at the documentation, you're doing show commands, you're doing commands on computers, you're trying to figure out how things are working. You take any address that's actually working out there and its associated mask, and you do a little math that I'll generically call the subnetting rules, you can find the subnet ID, the numerically lowest or first usable address, the last usable address, and the broadcast address, and that's what we're driving toward for our first 2 labs. And computers don't do it the way I'm going to tell you to do it. Computers use what we call Boolean math, and that's binary math, and of course processors rocket doing binary math. But for us humans, if we could find a way to do it with decimal math, that's one way that possibly you could be able to do the math in your head without having to master decimal to binary and binary to decimal conversions. If you'd like to master those conversions and do subnetting that way, it is fine. It's just not what I teach here in this class. All right? So what are we looking for? Any address that exists and its corresponding mask, find the subnet ID, subnet broadcast address, and the range of addresses as you see depicted here. So here's a subnet ID and mask. And could you take these 2 numbers and calculate the rest of the facts? That's where we're headed. So that mask that I just showed you in the title, it defines the prefix part and the host part. The mask is a 32-bit number. So just like the address is 32 bits long, the mask is 32 bits long. But it's very particular. First off, the mask has binary 1s in it on the left. If there are 1s in it, they are left justified. They are not interleaved. They are contiguous. Contiguous 1s on the left. And on the right, binary 0s. They are contiguous, not interleaved. They have to be by rule. And so all the 1s on the left dictate that in the subnet this mask is used with. So if you're using a particular mask in a particular subnet and it's got so many 1s in it, those are the prefix bits, all the addresses then, that's the bits that their values must be identical. Host bits are the ones that can vary from address to address to address. For instance, in the last few examples, where we said, hey, how about subnet 172.16.1, where all addresses must have the same first 3 octets? 3 octets, 3 times 8 is 24. That means you've got 24 prefix bits in your binary mask and 8 host bits, 8 0 bits in your mask, which dictate that the first 24 bits in all the addresses must have the same value. All right, so that's where the mask is defining things about an address. So there's that same mask, 24 1s. There's the prefix part by definition. Prefix part, same value in each address. Host part, different value in each address. Just written in slide form. So let's just say, look over here on the far right. Those are the first so many addresses in subnet 172.16.1 all the way down to the bottom to the last view, all right? And over here in the center are the binary equivalent of the numbers on the right, okay? Binary equivalent. So if I look at the first 3 octets over here, and I look at the binary values, they are identical. By definition, with a 24-bit mask, it says the first 24 bits must be identical in every address, and there you go. They're identical. Whereas the last 8 bits, they differ in some way, shape, or form in something in these last 8 bits. So again, confirmation of the meaning of those numbers. Turns out if we were to list the numbers, lowest to highest, the lowest number is the subnet ID, and the numerically highest number is the subnet broadcast address. And then everything in between is allowed to be used by a host. All right? Now, how big is that subnet? We could have counted those addresses, the ones in between the subnet ID and subnet broadcast address, and counted 254 addresses. In fact, that's the easy case, if you will, or that's using a relatively easy mask to do the math with. But because we see this mask of 24 prefix and 8 host bits, we take the number of host bits of 8 and do our little formula, and we can calculate that 2 to the 8 minus 2 is 254 usable addresses in that subnet. So as it turns out, you're going to want to be able to do powers of 2. I would say at least memorize up through 2 to the 12th. Here's a few of them. Your reference page, that some of those links to the right will point to, gives you a powers of 2 reference as well. But this gives you the 2 to the h minus 2 value over in the right-hand column, just in the slides for reference as well. All right, that's enough to make you dangerous with the concepts behind subnetting. And now we're going to move on to talk about doing some math. I don't see any new questions there. Hang on while I'm doing a quick check. All right. Here's that third terminology reference. So if you're new to this and you're looking for something useful to review between in the class today and tomorrow, I'd say check out some of these terms. I haven't used all of them yet, but it's a good place to go for review. All right, learning stages. So this is something that's not subnetting. This is just how you can be more effective as a learner during class. All right, so here's the deal.